Hello, today we're continuing in our GCSE physics revision series looking at energy transfer. The key point here is that energy cannot be created or destroyed, but it can be transferred. There are different types of energy and you can move between them. You never lose energy, but you can change to different forms. The types of energy are electrical, as in a current, light, sound, kinetic, which is associated with movement, nuclear, thermal, which is associated with heat, gravitational, between two masses, elastic, which you would find in a spring when it is stretched, it has energy, and chemical, such as you might find it in a battery. The last three of these are, as it were, stored energy. The energy isn't actually doing anything, but it has the capacity to do something, and for that reason we call it potential energy. Energy in a battery has the potential to provide a current flow. It won't until you connect it up. Energy in a spring will only become apparent when you let go of the spring. And there are all sorts of examples of energy transferring from one form to another. For example, in a generator we've seen that you use heat to turn the turbine, which turns the generator, which produces electricity. So heat becomes electrical. Or in a light bulb, electrical energy becomes light energy. In a hairdryer, electrical energy becomes heat energy. In a loudspeaker, electrical energy becomes sound energy. When something falls to the ground, gravitational potential energy turns into kinetic energy. But although energy is never lost, we have to make the distinction between useful energy and wasted energy. Consider a light bulb. When you switch on the light bulb, what you want it to do is to give you light. What it will also do is to give you heat, and that isn't usually what you want. So the light is the useful energy, the heat is the wasted energy. So if you take any system where you're transferring between different types of energy, you will have a certain amount of energy that you put in one form, and then you'll get some energy out, which is what you want. That's the useful bit of the energy. But invariably you'll get energy out that you didn't want, and that is the wasted part of the energy. And as we shall see, in many cases that wasted energy is heat. Now we define the efficiency of any unit which is going to convert energy from one thing to another as the efficiency is equal to the useful energy out divided by the total energy in times 100, and that gives you the efficiency in percentage. So in other words, you take the useful energy out and divide it by the total energy in, and that gives you the efficiency of the machine, because that tells you how much of the energy you're using is actually giving you what you want. And by definition, the remainder is actually wasted. Heaters are often very efficient. They're the sort of things that take coal, fossil fuels, electricity, and convert into heat. And heat is what you actually want. It's to heat a room, for example. So quite often you find that those are close to 100% efficient because all of the energy goes into heat. Occasionally you may find that it goes into light energy as well, which you don't particularly want, but most of it is heat. Sometimes it's a moot point whether the energy is wasted. Let's consider boiling water in a saucepan. There's my saucepan, there's my water, and I've put it on the gas hob on the stove, and the heat is boiling the water. So I want that heat to cause the water to boil. But of course, if I put my hand close to the saucepan, I will feel the heat, because some of that heat is of course escaping into the room. Not all of it is going into raising the temperature of the water. Now, is this wasted heat or lost heat or not? Well, it might be if it's a warm summer's day and I don't need to heat the house. But if on the other hand I do want to heat the house, then arguably this is actually contributing to warming the house. We need to think therefore about the question of cost effectiveness. It may be that a low energy light bulb is 4 times more efficient than an ordinary light bulb. In other words, it uses more of its energy for light, which is what you want. But it also costs more. So the question is, what's it better to do? Buy a high cost, low energy light bulb that's more efficient, or buy a low cost, ordinary light bulb that's less efficient? Well, here's the way to work it out. Let's suppose it costs £4 more. So the low energy light bulb costs you £4 more than the ordinary light bulb. But let's suppose that it saves you, because it uses less energy, £12 per year in energy costs. Then we can have a concept called the payback time. Because effectively what you've done is you've spent £4 more than you would, but a year later you'll have saved 12. And the payback time is the initial additional cost divided by the annual saving, and that is 1/3, or if you like, 4 months. So the payback time is 4 months. In 4 months you will have recovered the extra £4 outlay because you will have saved £4 in electrical costs. Provided the light bulb is still going, after a year, even though it cost you more than £4, even though it cost you £4 more to buy the bulb, at the end of the year it will have saved you £12, so you're £8 better off. Of course, a really good design of system would take the total energy in, the useful energy out, and if it's really good, it'll take the so-called wasted energy out and try and reuse it. And if that energy out that you don't really want is, say, heat, you might be able to send that to something like a heat exchanger, which will give you some useful energy back. Some of you will be asked to draw what are called Sankey diagrams. Sankey diagrams are, as it were, scale diagrams to show how much energy is useful and how much energy is wasted. And the way you draw the Sankey diagram is you draw an input which has a certain width. And you normally would draw this on graph paper. Let's say that the width is A centimetres, and that's the total energy in. And then you have your first useless energy out. That will have a width, we'll call that B. And you might even have some more energy that's lost. And we'll call that width C. And then what you're left with is the actual useful energy out, which we'll call width D. Now this might be a motor. So you put electrical energy in, you will get some heat energy out that you don't want, you'll get some sound energy out, the motor will make a noise that you don't want, and you'll get some kinetic energy out which you do want. And the idea is that the width of the E in is A must be the sum of these other widths, so that will be B plus C plus D. So on your graph paper you will ensure that B comes out first, and then there's less energy left, so that's why this goes up further. In fact, the distance between here and here is B, to reflect the fact that B's worth of energy has now gone down, as it were, as wasted. And then you've got another outlet here which is wasted, and so the difference between these two distances here will be C, to reflect the fact that C has been wasted. And then what you've got left is a width D. And that's called a Sankey diagram. It's just a way of showing energy input and then the wasted outputs and the actual required outputs. by reflecting the proportions of those by the widths of the arrows that come out. Let's suppose that in this diagram A was 1 centimetre, B was 0.5 centimetres, C was 0.3 centimetres, and D was 0.2 centimetres. What that would mean is that effectively 50% of your energy was coming out as heat, 30% was coming out as sound, and only 20%, because it's 2.2 compared to 1, was coming out as kinetic energy. So if you were asked what is the efficiency of that system, which of course is equal to the useful out divided by the total in, that's going to equal, the useful out is 0.2 and the total in was 1, and then of course you always multiply by 100, and that's 20%. So the efficiency of that machine would be 20% if you were given those values for the Sankey diagram. So here's a question. We've got a kettle. The kettle takes 200,000 joules of energy in, and it deposits 10,000 joules of energy out to the room. In other words, that's wasted. So what's the efficiency? Well, the efficiency, of course, is defined as the useful energy out divided by the total energy in. Well, we know what the total energy in is. It's 200,000, so that's going to be in the denominator. What is the useful energy out? Well, it's the total energy minus the wasted energy. So 200,000 minus 10,000 is 190,000. So that's the useful energy that is coming out. And that is 90, oh, you multiply that by 100, of course, and that will give you 95%. So the efficiency of that kettle is 95%. Here's another exam question. We have a light bulb, and we're told that the light bulb is 10% efficient, which means 90% is wasted. If 2,000 joules is given out, in other words, that's the useful energy, how much is wasted? Well, now we have to recognise that efficiency is the useful energy divided by the total energy times 100%. The efficiency, we've been told, is 10%. So we've got 10 is equal to the useful energy out, or we've been told what that is, that's 2,000, divided by the total, we don't know what that is, times 100. If you rearrange that, you'll find that the total, and you must be able to do this manipulation, is 2,000 times 100 divided by 10, which is 20,000 joules. So that was the total energy in. And we know that 2,000 joules was the useful energy out. So the wasted energy is going to be 20,000 in minus the 2,000 useful out, and that's going to be 18,000 joules wasted. Well, I've actually got wasted there already. If you were required to draw a Sankey diagram for that, you will remember the three values. You've got 20,000 in, 2,000 useful out, and definition 18,000 wasted out. Then you draw a Sankey diagram where the width of the input represents 20k. So you'd have a scale, you might say 2 centimetres would be representing the input. Then you need a wasted amount, which would be 18k. Well, on that scale, that would be 1.8 centimetres. So you would draw an output that would be 1.8 centimetres wide, and that is your wasted heat. And then, of course, you need to bring this line up so that this gap here is 1.8 centimeters to represent the energy that's been lost, and then what you would be left with is a line that would be only 0.2 centimeters wide, i.e. the difference between 2 centimeters and 1.8 centimeters, representing the 2000 useful output, 2000 joules of useful output that comes along the top here. So that's a Sankey diagram for the light bulb. A lot of what we do is designed to try and stop wasted energy. You want as much energy as possible to do the thing you want it to do rather than be wasted. So if you think about your own home and you think about heating your own home, there are lots of things you need to consider, because what you want that energy to do, however you're heating your home, what you want that energy to do is to warm up the home. You do not want it to be warming up the whole of the Earth's atmosphere. So you want to try and keep the heat in. Remember that the extent to which heat will be lost is to some extent determined by the surface area. Well, there's not a lot you can do about surface area of a house. You could perhaps live in a smaller house, but given that you've got a house, you'll probably want to do the best you can to restrict the amount of heat that gets out. So where heat could escape through the roof, you'll want to think about loft insulation. Where heat could escape through the walls, you're going to want to think about cavity wall insulation. Where heat could escape through the windows, you can think about two things. Double glazing. Double glazing often has a vacuum between the two panes of glass that restricts the amount of heat that can get away. And you can also put thick curtains up at the windows which trap the air. So there's a trapped layer of air both between the window and the curtains, and also the curtains themselves, of course, are made of fibre which trap the air, so stopping heat loss through the windows. You'll also want to worry about heat loss through the door, particularly at the bottom of the door where there are draughts, so you may want to put draught proofing in. And then if you've got a hot water tank where you're heating your hot water tank, you'll want to think about lagging that so that you stop the heat getting away from the hot water tank. All of those things will cost you money, but they should save you energy. And as we've already said, we've got this idea of the payback time is equal to the initial cost divided by the annual saving. So let's suppose that the initial cost of all these things was £5,000, but you got a £1,000 saving per year in your electricity bill. Then the payback time would equal the initial cost, which is £5,000, divided by the annual saving, which is £1,000, and that's 5 years. So it would take 5 years just to break even. But these things are likely to last, well, maybe for 20 years. And so for the first 5 years, you're just getting back the money you've spent. But thereafter, you will be saving money at the rate of £1,000 per year. Money that you would otherwise have spent if you hadn't done all those things to reduce heat loss. Sometimes you will find things that are designed to prevent heat loss described as having a U value. The higher the U value, the greater the ways in which it can prevent heat loss. So you want a high U value. You might, for example, find that a duvet that you have on your bed is rated at 0.75. That's a high rating. It means that you'll be warm in bed because the heat will not escape. You might find that loft insulation is rated at 0.15. So it's not quite as good, but then you probably wouldn't be able to afford to lag your loft with duvets. You can have a thing called a thermogram taken. Now this is almost the equivalent to a photograph, except that whereas a photograph records visible light, a thermogram will record infrared. So it's essentially an infrared camera. And infrared is heat. So if you go outside your house and take a picture with a thermal camera and you get what's called a thermogram, then depending on how the image is produced, you'll be able to see where areas of your house are hot and where they are cold. Now, if it is hot outside, that means that's equivalent to heat loss. What you want is your house on the outside to appear to be cold, because then that means all the heat is being kept in. So if, for example, you often find that on a thermogram, the light colours, the reds and the yellows and the whites, that means that's heat or it's hot. On the other hand, the blues and the purples and the blacks indicate cold. So if the roof is, say, yellow on your thermogram, that means a lot of heat is coming out of the roof and you need loft insulation. On the other hand, if the walls are blue, well, that probably means not much heat is getting out of the wall, and therefore your walls are actually reasonably good at keeping heat in. On the other hand, if the door is red, that means there's a fair amount of heat coming out of the door and you need to think about draft proofing the door.